Hello Year 10. This is the second video about arcs and sectors and focuses on applying the skills that you have learned so far to solving problems. Here is a reminder of the two formulae that we know already, and I'm going to be using these to work through the examples on page 224 of the Caboodle textbook. So starting with example 1. Show that the shaded area here is given by this algebraic expression. That means that we're not going to get a numerical answer for this. We're going to have to work through the problem and finish with the answer in this form. Now you can see in the diagram that we have a large sector with a radius of big R, and on the inside a small sector with a radius little r that's been removed, leaving the shaded area behind. So we're going to need to do a subtraction. Because I've got two sectors, I'm going to do the working separately. So I'm going to start with the area of the large sector. Writing down my formula, theta over 360 times by pi r squared. Substituting what I know the angle is 45 over 360 times by pi times by, and in this case the radius of the large sector is big R squared. So I can't get a numerical answer, but I can simplify it. So this cancels down to 1/8. This is simply pi big R squared. So that's the area of the large sector. The area of the small sector starts with the same formula. And again, I substitute in what I know. So I know the angle at the centre of the small sector is 45 over 360 times by pi times by the radius of the small sector, which is simply still little r squared. And simplifying, I get 1/8 pi r squared. Now then, the shaded area is going to be equal to the large area take away the small area. Which in this case is 1/8 pi big R squared subtract 1/8 pi little r squared, which at the minute doesn't look very much like what it needs to be. But I can see I have got a common factor of 1/8 pi in both of these parts. So I'm going to factorise it, taking out a common factor of 1/8 pi, which leaves me with 1/8 pi brackets big R squared minus little r squared. Still not quite there, but you can see here I've got two factors. And I've got a quadratic expression here, and hopefully you can see that that quadratic expression is the difference of two squares. So I'm going to factorise the difference of two squares. So I still have my 1/8 pi on the outside, and then I have two brackets, big R plus little r, big R minus little r, the factors for the difference of two squares. And now it looks exactly as I needed to set it out. So I've shown that the shaded area after my subtraction is equal to this. Moving on to example 2. Example 2 says we have 3 identical pencils and they're held together with a band. The radius of each pencil is 4 mm, and we need to show that the length of the band is 8 lots of pi plus 3. So looking at what we've got here is a slightly simplified version of it. If I join the centre of all my pencils together, because they're identical, what I get is an equilateral triangle in the middle, which means that all these lengths are the same and all the angles inside are the same. Now these lengths are made up of 2 radius measurements. So that's 4 and that's 4, which means that the length of one side of my equilateral triangle is 8. That length there is parallel to the straight side on the outside of my shape. You can see the outside, the band around the outside consists of 3 straight lines and 3 arcs where it curves around the pencils. So the straight line here is parallel to one side of this equilateral triangle, which means that has got a length there of 8 millimeters, and it will be the same there and there. Now, because these are 2 radius measurements as well, and that are the same, then we're looking at a rectangle. We know that this angle here is 60 degrees because it's an equilateral triangle. We know the angles in my rectangles are 90, which means I will be able to find the angle for that part of my circle, so I can find my arc length. So I've got 90 and 90, there is 180, and 60 and must be 120 to also be equal to 180. So I have got 3 arc lengths where the angle is 120. So let's call this my arc length there. Let's call it L. So arc length L is going to be equal to, as my formula, theta over 360 multiplied by 2 pi r, where 2r is the diameter. So I've got 120 over 360 times by 2 pi times by 4, and simplifying what I've got there, I've got 1/3 times by 8 pi. Now, you'll notice that my final answer that I need to show is an exact value. Nothing has been evaluated using a calculator, so you don't need to be using a calculator here. So I've got one arc length is 1/3 of 8 pi, and I need 3 altogether. I've got this straight edge is equal to 8, and I need 3 altogether. So the length of the band is going to be equal to 3 lots of the arc length and 3 lots of the straight edge. Well, 3/3 are 1, which means that this is going to be just 8 pi, and that is 24. So we're very nearly there. It's not quite the same as what it is in the question just yet, but I need to make it that way. So you can see that 8 pi and 24 both have a common factor of 8. So I'm going to take out a factor of 8, leaving me with 8 lots of pi plus 3 as my length, which is what I needed to show. So that's that complete. There is a slightly shorter way of doing this, and that is, obviously we've got these 3 straight edges that are 8, but we have got 3 arcs that are 1/3 of a circle. So I could quite easily have just worked out 8 plus 8 plus 8 plus 1, the diameter of one whole circle, which is what I've done here, 3 lots of the arc length. Now it's your turn. So have a go at the questions in exercise 15.3a on page 225. Remember that the questions marked with an asterisk, the little star, are the extension questions. Okay, good luck, thank you, until next time.